As depicted in the previous clip, this is often a scenario that many hard of hearing individuals find themselves in. Once in a group conversation, they require the use of a translator. This translator could be a mobile device, or it could actually be another individual within the conversation. The use of the translator often takes away their independence in communication for that individual. This was the problem our sponsor came to us to solve. We came up with the idea of having a microphone subsystem that wirelessly connects to an iPad. And on that iPad is an iOS application. This application had three main functionalities. The first being to translate audio in real time, and that we defined as being less than 3 seconds. The second being to indicate the direction of the speaker, and this was done via an arrow on the GUI. And thirdly, we wanted to be able to identify who was actually speaking. So we had a voice recognition component of our system. And this was done by having a pre-existing voice profile. And we set that upper limit of voice profiles to be 20. Now, throughout our design process, we came up against many obstacles. The first being we were tasked with not being internet dependent at all. So we had to have a wireless design that required no Wi-Fi. The second being the transfer of our neural net to the iPad. Now, this was our voice recognition component that Jason will talk about later in the video. And thirdly, we also realized that our Bluetooth connection that we had between our Raspberry Pi and our iPad was not going to have the correct bandwidth to be able to actually transport audio files between the two subsystems, which led to our new idea of information transfer, which we decided to go with the message queuing telemetry transport that utilizes an ad hoc network that we could create using our Raspberry Pi.
This is our system block diagram, and it will describe how exactly our system is going to work. We have a speaker and the user of the system outside of the system boundary, and there are two sections inside the system boundary. Firstly, there is a 3D printed case that will include a battery, Raspberry Pi, and 2 microphones. The battery and 1 microphone will be connected to the Raspberry Pi using pins, and the other microphone is connected to the Raspberry Pi by a cable. The other part inside the system boundary will be the iPad or the GUI. The Raspberry Pi would communicate and send data to the iPad through MQTT. This is how the system is going to work. The speaker will give a voice input, and the voice will be recognized and translated into text, and also the location of the speaker will be defined. And all of those subsystems will be defined using multiple software packages. And all of these data would be available for the user of the system in the iPad or the GUI. And those data are considered as the output of the system.
So to fulfill one of the main 3 functionalities of our device, namely the directionality component, we landed on using ODAS, which is an open source library written in C++ that hosts a bunch of sound localization algorithms that you can configure to a number of microphone inputs based off of your specific microphone device. Now we're using the Matrix Voice, which is a 7 microphone array in a circle with a single 8th microphone anchor in the center. And as such, we configured this to our ODAS algorithm. We take all of the relative input of the speaker, whose audio waves traveling towards the actual microphone array have different amplitudes for each individual microphone that are getting hit on the actual microphone array. When we feed that into the ODAS algorithm, it gives us a relativistic position of where that speaker might be coming from. And it is fairly accurate, given to about plus or minus 5 degrees in one of our testing requirements. And from this information, we can send it via our MQTT server, which is hosted on an ad hoc network. So because we were unable to use a Wi-Fi direct or web server connection due to our end user not having a reliable internet access, we use an ad hoc network that directly attaches our Raspberry Pi to our iPad display. Now, MQTT is just a subscription-based service, much like email, where anytime new information is presented from the Raspberry Pi or the embedded hardware, it will post all that to a digital virtual topic that then all subscribing devices, our iPad, will then receive over the IEEE 802.11ac Wi-Fi card standard that the Raspberry Pi hosts. So it sends all this information over at extremely low latency and allows us enough bandwidth to not only send over this integer data, but also our audio streaming packets that feed into our speaker identification and our voice to text algorithms as well. So the two in conjunction with each other handle a lot of our testing, such as the angle tolerance, the filtration, as well as the frequency and amplitude sound tests that we have in our final report shown here on. We have a couple of demonstrations of this happening and some of the testing videos throughout the rest of the slides, as you will see.
To accomplish speaker identification, we decided to go with machine learning. Specifically, we implemented a residual neural network, which is a special form of a convnet in Python. We chose Python for research and development because of its success in machine learning and data science. Using Python was a huge help in researching and deciding what type of model and how many seconds we are going to need to feed this model in order to get an accurate prediction. In the final implementation, we actually did not use Python directly. We did convert our Python model to iOS compatibility using Core ML, but in the end, we decided to completely implement our speaker identification model using Swift and Apple's Core ML and Create ML tools. This made it a lot easier to retrain the model and interact with audio streams easily on iOS. This was something that was tricky to do using our converted Python Keras model. To accomplish voice-to-text translation, we also had to utilize machine learning. Originally, we tried to implement a model in Python, but soon realized the challenges involved in creating an effective voice-to-text model. The vocabulary an average human person knows is well over 5,000 to 10,000 words, and the vocabulary that these models need to understand to be effective can be in the range of 20 to 40 to 60,000 words. So not only is this a huge challenge building a model that can work with this data, it's also a challenge to acquire this data in the first place. The best use of our time was to utilize a system that was already compiled, a voice-to-text system that can already run on iOS. So for this, we decided to use Apple's speech framework, which allows offline capabilities as well, which is a relatively new feature because these machine learning tools, as I say, typically use large data and they need to have access to fast GPUs. Usually this is done server side. So these were all things that we were able to utilize to make our project possible.
Thanks for watching Team 22025's Design Day video, and we look forward to seeing you at Design Day on May 2nd.